Thank you very much for the invitation. It's a pleasure to be speaking here. So this is a 30-minute talk that is going to be structured as follows. I'm going to talk a little bit about the motivation behind this project. And while the project that I'm going to talk about is my own work, doesn't necessarily have to do with p-adic variations of modular forms, is motivated by a somewhat analogous work that is related to p-adic variations, which is work of Dermont, Lauder, Rogers. So we'll start by talking about that, and then move to my own work that is joined with Henri Dermont in preparation. So let me start with some motivation. I'm going to talk about things that have to do with triple product periods. So I'm going to start with triple of new forms, F, G, and H. New forms, levels, and F, and G, and H. And it will be sometimes convenient to consider that as of the common level and given their least common multiple. And I'm going to assume the following about these forms. So I'm going to take F, a weight 2 form, with direct character. And while this will not be an essential assumption, I'm also going to assume that the coefficients of F, the real coefficients of F are rational, so that I can think of this F as corresponding to an elliptic curve over Q. And for G and H, I'm going to instead assume that they are weight 1 forms. Well, inverse central character, this is an important technical assumption. So that I can attach to that a pair of RT representations. And what I'm going to talk about will have to do with the tensor product of this RT representations, which I'll denote as rho GH. That is going to be a 4-dimensional representation of the Galois group of Q, which I can view as valued in some number field L. And I can also view this representation as factored through a finite portion. And I'll denote by H the field cut out by this. So L and H are number fields. They play very different roles. Here, one is the coefficient field for this representation, and the other is where this factors through. So why do I want to put myself in such a specific setting? Because I want to say something that is relevant to the purchase and denial conjecture. So this is not great. To this arithmetic objects, I can attach a Hasse-Weil function. Of course, we expect a relation between the order of vanishing of this L function and S equals 1, if this makes sense. Well, a rank of global points of elliptic curves by this I mean the dimension of the vector space of the L vector space of embeddings of this representation of reg A. Insert L. But I put myself in this specific setup so that this Hasse-Weil function can also be interpreted as the L function attached to the triple product convolution of this modular forms, so that many more properties of these L functions are known to be true, for example, analytic continuation and functional equation. And another important property that we want to use is the connection between the central critical value of this function and triple product periods, which is known through the work of Harris and Kudla, Garrett, and Ichino, the specific statements. So this connects the central critical value of this guy. Can you guys see here? Is that okay? To things that look like inner products of certain choices of class vectors for G, H, and F. And the main statement being this central critical value vanishes precisely when all of these products vanish for all choices of class vectors. And this suggests that these guys should say something about the group of rational points of the elliptic curve when we look at this isotypic part. So we want to explore this relation directly by modifying maybe this guy here to say something about rational points beyond the L value, but something about explicit formulas. So this is the general picture. So what I'm going to assume throughout is that the sign of the functional equation is equal to 1. So this is a relatively mild hypothesis, which can be guaranteed, for example, by assuming that the conductors of F, G, and H are prime. But this is also true in other cases. So if we believe the Burton-Swinnerton-Dyer conjecture, this should imply that we are in a situation in which we expect the dimension of this guy to be even. I'm going to put myself in this scenario. So the first interesting case is, let's look at the situation in which we expect rank 0, because this is probably what we expect most of the time. And in this case, we have a theorem due to Darmon and Roger that tells us that if the analytic rank is 0, so the value is non-zero, then the algebraic rank is 0. So this was the sensitivity part is actually true. So the question is, can we modify these notions of triple products to say something that is interesting beyond this case? So I'm going to assume for the rest of the talk But this guy is zero. So that we expect the rank to be positive, and we want to say something about rational point. Okay, so this again implies the work of Harris and Kudla that I mentioned before, that all of these triple products here are going to vanish identically. So these are not going to be the interesting thing to consider, but we want to consider some sort of variations of those that give us something interesting. So I will first describe this P-adic setting, and then move to what I call the Tame setting. So in the P-adic setting, I want to fix a prime P that I'm going to assume does not divide any of the conductors. And I also want to pick one between G and H and treat them a little bit differently. So I want to break the symmetry between the two. And for one of them, I'm going to pick G. I'm going to choose a P stabilization, which means choosing a choice of UP eigenvalue. So that we get G alpha, a P stabilization. And I'm going to assume that there is the P stabilizations are distinct, so that my Galois representation of P is distinguished. So Thurman, Roger, and Lauder define this sort of analog of the classical triple product period in this setting as follows. So instead of, I can think of this guy as, roughly speaking, multiplying G and H and looking at the F isotypic component, maybe divided by the Peterson norm of F. I'm going to do something slightly different. I'm now going to take F, take it a common primitive of F, and this is going to give us an overconvergent form. F at weight 2, this is going to have weight 0. Of weight 0, I'm going to multiply this guy by H, by this H or another choice of test vector. And I'm going to take an ordinary projection of this guy. So this product is going to give me an ordinary, once I take the ordinary projection, weight 1 over convergent modular form. I'm going to trace it down to the level of G. And now I can take this guy and look at the isotypic component with respect to G. So I'm going to do another process. P G alpha tilde. H tilde, depending on the choices of best vectors, and we see that the role of G alpha is a little bit different from the one of F tilde and H tilde in here. What do I mean by this? So this will be the map that extends over convergent forms level and G to the generalized eigenspace attached to G alpha.
This is an infinite dimensional space?
Huh?
It's an infinite dimensional space.
What is the ordinary part first?
It's infinite dimensional space?
Yeah. Yes.
Yeah,
It's the ordinary part. No.
it's infinite dimensional.
No.
It's infinite.
No.
Oh, these are only classical forms. So this is primarily the composition theory.
No. These are not classical. They're over convergent, but ordinary.
So it's infinite dimensional.
Fine.
I just want to clarify this in pi G is the primarily decomposition theorem. It's just on finite dimensional space. You just take the Jordan decomposition.
Yeah, if you want. Yes.
Sure what you're doing. Okay.
It's I'm localizing at a maximal ideal. If you
I just wanted to make sure you're doing
Yes.
this in a finite dimensional vector space. Okay,
Yes,
okay.
that's correct. Okay, so the point here is I can do this. I don't know exactly where I'm going to land. So this is going to be an overconvergent generalized eigenspace. Can I describe this explicitly? So what is this guy? So it's the generalized eigenspace for the system of eigenvalues of G alpha. So it certainly contains G alpha, but it might be bigger. So how do I characterize the two situations? So this is going to be equal to exactly G alpha. When, if and only if the eigencurve is a tau over the weight space of G alpha. And this condition was characterized explicitly in the work of Ladin with Joël Belaïch in terms of the image of the projective image of rho G. But sometimes it is not just that. There are sometimes the eigencurve is not at all over the weight space, and then this is certainly contains at least one extra form, and I'm going to call this the exceptional case. Yes. So this, in principle, might be bigger than two-dimensional. In concrete examples, it doesn't seem to be, but let's assume that it's two-dimensional for now. And I can think of the action of Hecke operators in this space as having a form like this, where this guy is the eigenvector and this guy is the generalized eigenvector. Right? But in the setups, Roger and Lauder formulate a conjecture that relates the P-adic triple product period to sort of regulators of elliptic curves in right 2. So let me that with the shape of the conjecture. Let's say that we're not in the exceptional case. Then the triple product period is related to, and I'm going to explain in what way is related to a regulator to a regulator of global points where the elliptic curve attached to this choice of Galois representation that depends on the choice of stabilization as well, up to a P-adic period that only depends on G alpha. But the point is, either way, this is going to be a multiple of G alpha because in this exceptional case, this is all of the eigenspaces. So there is no other choice. And the symbol I'm writing here means this is true up to L rational multiples. And this L rational multiples might be zero, but the point is this is not identically zero for all choices of test vectors if this is non-zero. Okay. What happens in the exceptional case is a similar formula is true. So except that this is true, this is going to be the coefficient of this generalized eigenvector G alpha star. Now modulo the actual eigenvector.
Can I
Yes.
just ask a question?
Yes.
Why is the exceptional case, why is it two-dimensional and not more than two-dimensional? Why is it two-dimensional?
Why is it two-dimensional? We don't know. In concrete examples, this is computable because it's ordinary forms. There are some partial results in of Adele Bettina about why it should be of that form, but it's not super clear conceptually.
Formula should be true in for any rank. So we got
So let me tell you what the regulator is.
okay.
So-
Not-
yeah,
okay.
this is built into like the statement.
Can I ask a question about the interpretation of the formula?
Yeah.
So it's true up to multiplication by L cross.
Yes.
So how do you normalize G star alpha?
That's a good point. So a lot goes into the normalization of this this guy. You need to define some L rational structure on the quotient. The way you do it is to describe the generalized eigenvectors appearing here in terms of L units in the field cut out by the adjoint representation. But yeah, it's a very subtle point. Thank you. Yes. So not going to be too precise about what this regulator is. But the point is that this is going to be a 2x2 regulator. That is defined to be zero if the rank is greater than 2, which was T is greater than 1 in the notation I was using. And if not, it involves the images of global points that we construct by constructing global points in here. This construction depends on the choice of G alpha, to be precise. Looking at that locally at P and taking a formal group logarithm of this guy. This is going to be a P-adic value, but then we make a conjecture up to L rational values, that L is global. Okay? So this is the rough idea of what kind of ingredients go into the conjecture. So the thing I actually wanted to talk about, and I have maybe 3 minutes to do so, is related to the fact that once we make this construction, we are looking at these global points inside the local points, and we're taking this logarithm. This, by definition, kills the torsion part of the image of the global points in here. And the conjecture that I was going to formulate had to do with precisely that torsion part. So I'm going to try to say something about it the last couple of minutes. Thing for the period. So this construction is not at all P-adic, and we don't pick G alpha and we don't choose G over H. We can think of this construction in some sense as being F dominant. So we want to construct interesting generalized eigenspaces for the system of eigenvalues of F, but F is a way to form. So p-adically, we don't get very interesting generalized eigenspaces when looking at overconvergent forms. But we can instead consider congruences for F modulo our choices of primes. And that's what I'm going to do. So I'm going to consider congruences modulo L. And in order to guarantee the existence of congruences, I'm going to raise the level of F at the prime P that I have chosen before. So I'm going to consider S2F, S2, space on modular form, so level 2, weight 2 and level gamma naught F P with coefficients in FL. And I want to be in a similar situation as before, in which the space is not necessarily trivial. So I want an inclusion of F to be proper. How can I guarantee that? By putting myself in level raising conditions, which makes this generalized eigenspace bigger than F. So in order to do this, I'm going to assume that L divides AP squared minus P plus 1 squared. So this assumption is interesting because this is the order of points of my elliptic curve over P squared. So in order to make an interesting statement about these points, I'm going to choose a discrete logarithm of this guy, which just means choosing a morphism like this. And I'll take a minute to wrap up and make a statement. So in a way that is somewhat analogous to what I had before, I'm going to take now, I'm just going to take the product of F of G and H as before, and we know that the decomposition with respect to F in characteristic 0 is not very interesting, but I can look at the generalized eigenspace of this guy, mod L. And I'm going to call this L G H tilde. And the statement is now going to be, this is a conjecture, that the position of this guy inside the filtration for the action, Hecke action in the generalized eigenspace is related to the rank. So I'm assuming that this is 2T, the rank is even by assumption throughout the stock, that this lands as deeply in the, at least as deeply in the filtration by the Hecke action as the rank detects. And the second part of the statement is if the rank is 2, then this guy, as before, is related to a regulator for global points of the elliptic curve, but that keeps track of this torsion part. So rank is 2 means that T is equal to 1. Then this guy is identically 0, so 0 for modulo n squared. So this meaning that is 0 for all choices of test vectors if and only if this regulator that is a variant of the regulator I defined before, but is a mod P, is going to spit out a mod L number, is equal to 0. And the point is we formulate this conjecture because we can prove it in some special cases in which this regulator is described in terms of Higner points. And I'll stop here.